Hey, my name is Adam.
My name is Cole.
With this project investigating the viability of no-fines concrete for the use in residential slabs, the first question is, what is no-fines concrete? With a conventional concrete mix containing cement, water, sand and gravel, a no-fines concrete mix eliminates the sand or fine aggregates from this otherwise conventional mix. Some general properties of no-fines concrete include it being lightweight due to its reduced density, as well as the absence of sand and thus increase in voids resulting in a permeable mix.
For no-fines concrete to be considered viable in residential slabs, the compressive strength results must adhere to NZS 3604, requiring the mixes to have a minimum strength of 17.5 megapascals. With existing research commonly conveying no-fines concrete to have significantly reduced compressive strength, alternative testing methods were considered to help more accurately reflect the conditions experienced when in compression as a residential slab. To increase this viability, an incentive to switch to no-fines concrete was seen as a critical component to success. The environmental impact of the production and transportation of no-fines concrete compared to conventional concrete was quantified using existing research, utilizing multiple sources to ensure the integrity of any results and comparisons.
The alternative testing method trialled was the use of a plastic or steel mold encasing the concrete. A residential concrete slab under compression would experience constraining lateral effects from neighboring concrete particles, thus simulating this lateral effect a concrete slab would experience. It is also anticipated that the use of these lateral constraints would increase the compressive strength results achieved.
It was anticipated the environmental impact of no-fines concrete will be significantly less than that of its conventional concrete counterpart. This hypothesis is supported by the reduced cement content of no-fines concrete, with the production of cement being the primary carbon emitter during the production of conventional concrete. A further reduction in carbon emissions was anticipated through the elimination of sand, with the production and transportation of fine aggregates also increasing the carbon footprint of conventional concrete. This anticipated reduction was quantified considering cement production, aggregate production, transport, as well as other concrete plant processes. The use of recyclable fly ash as a partial cement substitute was also investigated, with the environmental impact quantified.
The compressive strength of the molds was to be determined in accordance with NZS 3112.2, which required the use of steel cylindrical molds as shown. 3 conventional mixes and 4 initial no-fine concrete mixes were tested, with the no-fine concrete mix providing the greatest compressive strength, further tested with partial cement substitution with fly ash. After the selected curing times, these molds were destructively compression tested using an off-standard compression tester.
As shown in this table, the unconstrained compressive strength results obtained suggested the optimum no-fines concrete mix ratio to be 0.3 to 1 to 6, with this being a ratio of cement to water to gravel. The use of both plastic and steel constraints saw an increase in compressive strength across the board, with the latter seeing a further increase. This greater strength observed using steel constraints was likely attributed to the reduced buckling effects the steel experienced compared to plastic. 2 further mixes with this optimum mix ratio were tested, with 15% and 30% partial cement substitutions for fly ash. Although the 15% fly ash mix saw significantly reduced strengths compared to all 4 no-fines concrete mixes, the 30% fly ash mix provided strengths not greater than the optimum mix without fly ash, but greater than our lowest no-fines concrete mix, this being the 0.4 to 1 to 6 mix.
The compressive strengths obtained for all no-fine concrete unconstrained and constrained mixes did not meet the required compressive strength of 17.5 MPa as per NZS 3604. However, there were numerous contributing factors that likely influence the integrity of the results, including curing method, mixing technique, material quality, and unavoidable human error. Recommendations are supplied for further investigation with the results obtained, although insufficient, showing potential to be viable.
Recommendations for further investigations are made, with these including utilizing more optimal mix ratios and increased constraint thicknesses. For example, a water to cement ratio of 0.25 in conjunction with a cement aggregate ratio not exceeding 1 to 6 could see an increase in compressive strength based on the results obtained from this investigation. The use of thicker lateral constraints could also help prevent buckling effects being misinterpreted as lower compressive strengths.